just kind of doing a little intro, and then I'll introduce these guys.
Good morning, good afternoon, good evening, wherever everybody is. This is Tim Baechle with Idealliance. I want to thank everybody on for joining today with the spectral curve, what it is and why it matters. I especially like to thank fellow moderator Ron Ellis from Ron Ellis Consulting, a great brand consultant, and our three panelists, Ray Cheydleur from X-Rite, Pantone, Jim George from Cross-X Color and Color Logic, and Mark Samworth with Esko product. With Esko. I'd like to make a quick note, and this is kind of unusual, and he doesn't know I'm going to mention this, but we have a very, very large audience today. Idealliance every year since 2005 gives out the Circle Award for Excellence, and this is for innovation and in the industry. And this individual has moved the industry, and it's a very unique award. And our success in our industry is based upon people giving their time and their support, the most unrenewable resource they have. And without them, we couldn't do what we do around the world. And I'd like to announce Ray Cheydleur as a Circle Award winner this year for advancement in collaboration, development, and progression of international standards. So, Ray, I don't know you're aware of that, so congratulations to you. And with that, I'll kick off the meeting to Ron.
Great. Wow. Congratulations, Ray.
Thank you.
Yeah. So my name is Ron Ellis. I'm a consultant. I work with Print Properties, which is Idealliance's committee that works on standards and specifications and user outreach, and also do a lot of G7 expert stuff. So I'm a G7 expert, train experts, but also go out pretty much every week and do G7 calibrations. I work with brands quite a bit too, and that's kind of what brought about these webinars when we were thinking about them in the beginning. And so the idea of these webinars is to give good information that we always hear people looking for and cover topics that people are trying to learn more about. I'm going to introduce our panel. Our panel is great. These are some of the best guys. And first guy is Mark Samworth, who I love listening to all the time. And he's Esko product specialist, but I think his title underrates what he does. So he's kind of a key guy. He's been involved with Idealliance for a long time, with the FTA and other groups. And he has 12 patents on screening and technologies like that. Super smart, spends a lot of time thinking about topics like this. And great to hear him. So he's a great person to listen to. I think you guys will enjoy listening to him. Our second presenter is James George from Cross-X Color Logic. And he's an application specialist, but he's got over 20 years in the printing industry, working from both the design and the customer end all the way through rendering and working with things like we're talking about today, spectral data, and getting the best possible interpretation as you go through print. And then Ray Cheydleur. And Ray Cheydleur I've watched for years and years at print meetings and Print Properties and CGATs and print standards type work, and pretty much you've been at X-Rite forever. So if I ever have any technical question, he's the one guy I think of who would know the answer. So the deepest, hardest question about standards, color, instruments, this is the guy who pretty much knows the answer to almost everything. I'm sure there's things you don't know, Ray, but from my perspective, you pretty much know everything. So our agenda today, what we're going to go through is we're going to start off with Mark Samworth, and he's going to talk about spectral data, and he's going to give kind of an introduction to it, just sort of the starting from nowhere. Because spectral data, when I talk to customers, they get LAB, but spectral data kind of is a fuzzy spot for people. It's one of those things where they don't really know what it is or what to do with it. So he's going to kind of go through the overview of what it is. Jim George will talk about spot colors, rendering, conversion, and what the potential of this is and what it gets used for. And then Ray Cheydleur will talk about other uses. He's involved in things like how ink is made, also standards, and how the application is done today. So we have three different topics, starting from the beginning to how people might use it to render color, to other types of uses for it too, and how it fits into standards. Before we start, I'm going to spend about 2 minutes talking about BrandQ, and then we'll get right into it. Each presenter is going to have about 10 to 15 minutes to kind of just give a little teeny topic, a little bit of it, and explain it. And then we're going to go from there to questions at the end. We'll have about a 15-minute question and answer session. As we're going through this, you can use your chat window to send in questions, and those will go to Steve Ballinger. He'll tally those up, and at the end, we'll use those and kind of run through those during our Q&A. This webinar idea is sponsored by BrandQ, and this is Idealliance's program for brands. And the whole idea of it is communicating, teaching people to communicate, educating the supply chain and the brands, and helping people understand how to measure and validate color. We work with lots of partners, so the companies that are on here, like X-Rite, Esko, and ColorLogic, are all partners that we work with in this program. They supply demo software, instruments, and knowledge, and so they've been very helpful with this. You can see Educate. This is a class that we did, and these are a bunch of print buyers learning about color and how to measure and how to talk to their suppliers about color. Communicate. People here looking at and talking about what should color be, how do they explain it, how do they express it. And then Validate is all about measurement. And in the class, we do lots of live measurements, 50% hands-on. So teaching people how to measure, differences in what you can ask for and what can be done. So with that, I'm going to move into our agenda. We'll start off with Mark Samworth. And Steve, can you flip it over to Mark?
All right. So thank you, Ron, and great introduction. Yep. Can everybody see my desktop?
Yes. Now we can.
Now you can. Right. Okay. Hey, I should start by congratulating Ray Cheydleur for winning the award for helping the Idealliance in the industry. That's great news. I lied to Ray yesterday, and I shouldn't tell him that I lied to him. But Ray, I wanted Ray and Jim and I to get together just to talk about, to make sure that our topics kind of went together and that it flowed nicely. But really, I wanted Ray to check my talk to find out any technical inaccuracies, right? I mean, he didn't even know that. He thought we were just talking about the flow. So, so I know I have everything correct that I'm about to tell everybody, because Ray saw it, and actually we fixed one or two things, but I'm never going to tell anybody what we fixed here. So, okay, so as Ron explained and Tim explained, I'm going to give kind of an overview on spectral data, spectral measurement. And then we're going to have Jim and Ray get a little bit more specific on how this technology is used, right? If anybody has ever even investigated, if you type in color measurement into the internet, or you go to a seminar at X-Rite or the Idealliance, there are literally hundreds of ways to measure color. Now, we're not going to talk about hundreds of ways in the next 10 minutes. We're going to talk really about 4 ways, and mostly about spectral data. But really, all color measurement started with density. And if you think about it, you can kind of take an instrument approach from this, because you could be wondering, well, why is the Idealliance having a seminar targeted for brands based on spectral data? And there's numerous answers to that question, but one answer is that all the instruments that we use today measure spectral data. We start from that. But they didn't always all measure spectral data. If you look back 10 years ago, not 10 years ago, let's say 30 years ago, 20 years ago, 1990s, that was one of the dates I got from Ray. He said, yeah, that's about right. We were not measuring spectral data. We were measuring density. And today, you can use a spectrophotometer to measure density. You can still do that today. It's done very commonly in the press room. But you cannot use a densitometer to measure spectral data. But let's just kind of look at a densitometer. Let's look at what it's actually doing. It's shining light on something, usually a patch of ink, right? You could think of it as solid ink. And it's measuring how much light comes back, right? So to use these technical terms, there's your light, your incident light, and then there's your reflected light, the amount of light that comes back, right? And it can measure tints, 25, 50, 75, or 100. Most of us, when we start measuring density, if you go into the press room and you say, what is your density? They're going to tell you the density of the 100%, the density of the solid. So sometimes when I do color seminars, I actually show people different print samples. And even on the screen, I'll get Pressman to guess, okay, what are these densities, right? And it's kind of funny, you know, because do these really have a density? Well, no light's being reflected. This is all emitted light, right? But they still have some perceptual kind of appearance. And it's amazing how close some of the Pressmen can get. But let's talk a little bit about what that really means. What is a densitometer doing? It's shining light down, and on these patches, some light's being reflected back. And as you can see, as you go from the top to the middle to the bottom, less and less light is being reflected back. So if we look at that top one, in that solid area, 100 units of light are being shined on the substrate or on the ink patch. 16 units of light are coming back that the photocell in the spectrophotometer measures, right? So you could call that a reflectance of 16%, right? Real simple. And if it weren't for these two, let's say, photographers or photoscientists in England, one named Herder, the other named Driffield, the whole world might be using reflectance meters today. And a densitometer might just tell you how much light's reflected back. But for a bunch of different reasons, and if anybody sends an email to the Idealliance, I will actually answer these reasons. If anybody really cares, you probably should not care. They decided not to report reflectance. They decided to put it into these mathematical log-based 10 equations and out pop a different number, density. So that value right there, the most common way, you could say it has 60% reflectance. Nobody would really know what you're talking about. Or you could say it has a density of 0.08. Now, the reason I mention this, pretty soon I'm going to talk about spectral data. And everything in spectral data is talking about the reflectance, not the density. So we're going to get into that. And there's another patch, much less light is being reflected. Instead of 15 units or 16, whatever it was 6.3. That has a density of 1.2. And if even less are reflected, you know, there's lower reflectance, 2.5%, that has a density of 1.6. So if you look at these, the less light being reflected back, the higher the density. And just to put some parameter on this, those of you who are familiar with the Grackle recommended solid is 1.7. So even a little bit darker than that bottom one. But you could really think of it as density quantifies black and white. You could say, this would sound kind of weird to say, you'll see it's less weird in a second, but density really measures the amount of white light reflected back. When you measure black density, you're measuring the amount of white light reflected back. So then the first question is, how do you measure color? I print not just black, I do print black, but I print cyan, magenta, and yellow as well. And if you get into the color triangle, this shows you the relationship between the colors of light and the colors of ink. And when I teach classes at Clemson or RIT or Cal Poly or Idealliance, work with the Idealliance, the only note I ask people to take is a color triangle. If you want to learn color, that will be the most helpful thing in your entire career you can know. We spend about 10 minutes on that. Here I'm going to spend about 10 seconds on that. But you can see that cyan and magenta make blue, right? Magenta and yellow make red inks. Yellow and cyan inks make green. So you can flip this around and look at light. Red light and blue light, look at the two sides. They connect at the point labeled M. Red light and blue light make magenta. Blue light and green light, look at the point of the blue and green, make cyan. And green light and red light, this is the one that tricks everybody. These are lights. The more light you have, the lighter you get. Green light and red light make yellow. And part of what Ron asked me to talk about was a little bit on trying to make looking at spectral data intuitive. I'll talk a little bit about it. Jim will talk about it next, and Ray will all three address that a little bit. But if you want to measure density, if you want to measure the density of cyan, look at cyan, you're actually measuring the amount of red light reflected back. So if you only shine red light on it, or you filter out everything coming back except the red light, it will make cyan appear as black, right? Just looking at the red light. And if we want to take a look at magenta, look across from magenta. When we measure magenta, we put a green filter over it, which means we're only looking at the green light that's reflected back, right? So a green filter makes magenta appear as black. You can think of it that way, whatever way you want to think about it. As you can kind of see where I'm leading up to here, doing all this is kind of cool. There's nice slides here, but we're only really getting 3 bands of light. And there's really an infinite number of colors that human beings can see. So if we want to measure yellow ink, put a blue filter over it, we're measuring the amount of blue light reflected back, right? So if you look at the color spectrum, you know, the rainbow, according to the densitometer world, it has three big sections. It's either blue light, or it's green light, or red light. When you report a density, like a cyan density of 1.4, you're reporting how much red light is reflected back. Then it has to throw it into that log equation because Herter and Dripfield, those Englishmen 100 years ago, thought that was a good idea. And we get back to these different numbers. But most of the world is not trying to really measure how much ink is being put on a press sheet. That's what pressmen are interested in. In the brand world, we're interested in how does it look? How does a human being see that? And a human being sees a lot more than just three bands. You know, these three bands will tell you how much cyan, magenta, and yellow ink are on there. But what we really want to do is to be able to measure a lot more bands in that color spectrum. And when you start to measure more than three bands, you call that spectral data. And Ray actually gave me all the updates on yesterday, in our talk yesterday. He gave me all the updates on the number of different bands the different specs are aiming for. Now, my talks here, I'm going to do all of these talks showing you these bands 20 nanometers apart. But all the current specs are either 10 nanometers apart, which means I'd have twice as many lines. I'm breaking it up twice as many times. And the future is 5 nanometers apart, breaking each one of these into 4. But I still think the graphics look better breaking it into 10. So we're going to look at a spectrophotometer. We're going to look at spectral data as you measure on a spectrophotometer. So you can think of this, it's the same mechanics in terms of illumination and a light sensor, but instead of having a filter, you can kind of think of this as being maybe a prism, right? For those of you who know the Pink Floyd album cover of Dark Side of the Moon, or it could be a refraction grating if you look at a CD, right, on the side tilted toward the sun, or it can be a series of filters, but a lot more than 3 filters. You need many, many filters in there. And you can be very selective in what part of the color spectrum you want to measure, right? So spectral data comes when you start to quantify how much in each band of the spectrum, how much light is being reflected. So they don't turn it back into density. 93% of the band at 640, it was reflected back. That's just reported as 93%. And if you think about it, you know, what is the importance of spectral data? Spectral data you can kind of think of as the DNA of color. If 2 colors' spectral curves match, they will match each other under every single light source in the entire world, including the sun, right? If 2 colors' spectral data does not match, their spectral curves can be different, they will match under some light sources, or you should say they could match under some light sources, but they might not match under others. That's called METAMERISM. Jim's going to talk about that, Ron, and Steve's going to talk about that as well. But spectral data, you can think of it this way. If their spectral curves match, they will match under all sets of conditions. That's not true with LAB. If 2 colors' LAB values match, they may only match under that one set of conditions. You could have 2 colors where their spectral curves are different, the LAB values match. They will match under one light source, let's say D50, but they will not match under another light source, let's say D65. And I know Jim has some examples of that. But if you want to try to make this a little bit intuitive, if you look at that spectral curve and you think about my color triangle, a whole bunch of light in the red's being reflected with a little bit in the yellow and green. So the eye's going to see that as kind of a yellow shade red. If you look at this spectral curve, a whole bunch of data in the blues being reflected and a whole bunch in the green and some in between green and blue. And when you're, you know, what's kind of interesting, there is no cyan cone in your eye. In the human eye, there's only red cones, green cones, and blue cones. So when a blue cone and the responses of the cones, to get a little bit geeky, actually overlap. So when your blue cone is being stimulated and your green cone is being stimulated, you get the perception of cyan. So if you want to try to understand how that color works, blue and green make cyan an additive color. If you see a spectral curve that has a lot of blue and a lot of green, it's going to give you the perception of cyan. This is kind of the weirdest one. There is no color in the rainbow. You know, some people say the rainbow contains every color you can see. That is a false statement. The rainbow contains only colors that you can see with those bands stimulating something in your eye, right? To get the sensation of magenta, there is no magenta in the rainbow, right? To get that sensation, your blue cone has to be stimulated and your red cone has to be stimulated, but very little or no stimulation of the green cone. And then you'll get a perception of magenta, even though it doesn't really exist. So those of you who want to kind of understand spectral data, you've got to use the rules of RGB. A lot of blue, a lot of red, red and blue together give you the sensation of magenta. So the traditional use for spectral data was really for geeks, engineers, because spectral data is used to calculate all the other metrics. Today, every density measurement you see came from a measurement of spectral data using some math to convert it. But we'll start with the spectral data. And from spectral data, we're going to convert that to something called XYZ. Now, this is not even used anymore for any practical purposes. XYZ is used to calculate other metrics. And the two common metrics that XYZ is used to calculate are LAB and LCH. So LAB is we could, and Ron and I were talking about this, we could have another webinar based on LAB and LCH, because LAB and LCH are actually the same thing. And LAB and LCH correlate much more to how your eye actually sees color than density or TVI or any of these other metrics. And they're actually kind of simpler to work with in some ways than spectral data. So sometimes it's best to work with spectral data. Sometimes it's best to work with LAB and LCH. We might have a separate webinar on LAB and LCH. And really what's kind of interesting is LAB and LCH are actually the same color space. It's all coming out of the CIE LAB color space. But one of them is expressed as Cartesian coordinates, XY. They're not labeled XY, they're labeled A and B because XYZ was already taken by the CIE. The other is a polar coordinate system where it's an angle and a distance. And there's advantages to both of these, and perhaps we would talk about that. But the future use is to use spectral data as a format for all color. So going forward in the future, every color measurement you see should have, if all of our software standards comply to it, spectral data underlying that. Now, you may use the spectral data, you may not. You may care about it, you may not. Here's an ink book in an Esko product called Color Pilot, and you can see that ink, Pantone 185. Trivial point is that happens to be the most common color in the world. And its spectral curve you can see on the bottom, a little bit different than the graphs I showed you. But you can see very high reflectance in the green and even more in the red, giving us the perception of a yellow shade red, right? Underlying that is the spectral data. Even if you want to create your own custom books, if you have a modern spectrophotometer, you can make ink books with any physical sample that you grab to measure. It's going to store it as spectral data, right? Press profiles. The ICC Max, and even the new profiles that the Idealliance is going to get involved with, don't want to give out timing on this, the data sets are all going to be stored as spectral data. So you open this up, and instead of just seeing, 7 columns, CMYK plus LAB, you're going to see a whole lot more columns. And Ray was telling us yesterday they even might go to 5 nanometers, which means twice as many columns as you have today, right? So this is getting kind of geeky, and that's about as much as we need today as an introduction. If 2 color spectral curves match, those colors will match under any light source. If you have the spectral data, you can calculate from that every other color metric that's available. And that's why we're going to be moving to spectral data. And with that, we are going to hand it back, and George is going to talk to us about how this data is used in the real world.
Thanks, Mark. Let's see. Can I share my screen? And
yep. Reminder for everybody, you can send in a question at any time by typing it into the chat box while Jim gets this thing set up. And Jim, you're all ready to go. Looks great.
Oh, thanks. And thanks, Mark, for that introduction to the spectral data. Is really good. And of course, congratulations to Ray. That's quite an honor. And Ray's been around, as they said, for years, more years than I care to know. Again, my name's Jim. I'm with ColorLogic, and for those not familiar with ColorLogic, we develop high-end color management technology and software. And I really like to thank everyone today for taking some time out, especially with the NCAA tournament games going on, to learn about something interesting like spectral data and how this was going to revolve around your print jobs and your designs. To start, let's look at a typical spot color. In this case, this is a reflex blue, which would be reproduced. And the current methods are kind of like in between. They work, but there are better ways to do things. Currently, spot colors can be defined in a PDF file with RGB, CMYK values, including lab and alternate color spaces. And only recently, lab values were included in PDF files. And even with that, it's been really referring to mostly the solid areas only. So again, like gradients and overprinting builds, it's trial and error, or even worse, what I like to call is you're proofing the job on press. And for most applications, when it comes to especially spot colors or certain types of gradients and overprints, Acrobat, Photoshop, and Illustrator, there's not really an easy way to view something like a reflex blue on screen without really highly specialized software. And if there are overprints or blues, you have some challenges there. And the gradients and looking at the files on the screen, it'll just be inaccurate. So for many print manufacturers too, it's just trial and error if you go the conventional kind of route, the lab, the CMYK conversions, or just, I call it the guesswork or whatever. And by including real spectral data, as Mark showed, you're going to get a higher and more accurate conversion. Most workflow today, they support or they have upcoming support for spectral data as well, such as ColorLogic products. X-Rite has Pantone Live, which is spectral libraries. Esko, CGS, Callis, GMG. They are all supporting now spectral data within their workflows, which is a really great thing for converting colors really, really accurately, and as you're going to see, on different types of substrates. And the most recent development, I guess, from a workflow kind of perspective, is that the PDF 2.0 standard is out. And that fully supports the CXF X4 data, which is a container for spectral data, which is what it's a standard that's going to contain data that different workflows can then interpret. It can also be used in things like, hopefully in the future, it will be used, Adobe is going to implement PDF 2.0, and it's going to have that and hopefully some, I call it later releases, but they promise that they're going to support PDF 2.0 fully, so that would be great. But that's a different type of seminar. What I'm going to talk about right off the bat here is METAMERISM. And just not to throw too many technical effects and technical terms at one shot, but really it's the interesting effect that happens when looking at a color or two colors specifically. And I'm not going to go into every single geek speak and technical explanation here, but clothes, walls, photographs, artwork that change color under different lights are all examples of METAMERISM. It really happens when two colors that are actually not the same and they look the same, because different wavelengths are affecting the color under certain kinds of conditions. And this is kind of an example of that. This is my super simple example. An example here is the light source inside a retail stool, and this is an extreme example, only emits blue and red wavelengths, for example. And the natural light outside is red, green, and blue wavelengths. Well, what would it look like? And it's obviously an exaggerated example, but if you only had a purple light inside here, your object, if you had a green object, it would look black inside. Outside, it would look normal, or quote normal, because all the different wavelengths are hitting the package at once. It's exposed to all three. So red and blue are absorbed under natural light, but green wavelength is reflected and picked up by your eyes, so outside the package is green. So why is this an issue for printed products, or spot colors, you might say? you know, what I'm doing now as a designer or a production artist, it seems to be working. But in terms of that, if your design has a lot of spot colors defined with lab, CMYK, or even near neutral or dark colors, it's definitely possible to avoid it. So some of the benefits here is to just basically use spectral data. And the benefits, we can get better prediction of colors, which of course is going to be a better outcome and a higher quality product at the end. You're going to need less human intervention and fewer pre-press changes, which then, of course, for brand people, you're going to get a quicker product cycle. Automation is really key here, and a lot of color management now is fully automated. The days of manipulating things by hand in a dark room in Photoshop and Illustrator, yeah, there are some print manufacturers who do that still, but for the most part, the bigger players are really moving into automation in a big way. And one of the reasons is because of spectral data and the ability to predetermine what the final products are going to look like with a minimum amount of intervention. And of course, here I'm going to show just a quick demonstration. This was Marker was referring to. This is a overprint with a red and the spectrum, and this is the same color measurement on two different substrates. And you can see the large spike here, how much that the brightener in the paper is affecting the color purple. So it's really affecting it in a really strange way. Strange, but we can compensate that if we actually know what the measurement is. And then again, and I'm going to talk about I talk about standards quite a bit. Excuse me. With a purple range, you know, it's obviously going to be a big deal. But we can also calculate overprinting colors a lot more accurately on light and dark substrates. And that's what this strip is demonstrating down here. So not only can we do it on like a 0 to 50 on a white background, we can also measure on a dark background. So those areas of your designs would really, really benefit from using data, from using spectral data. And I always like to talk, again, I'm talking about CXFX4, and Ray is usually the guy who likes to talk about standards, but I'll just say that that's really the key here, and that's like one of the big developments recently into integrating CXFX4 or spectral data into standard print jobs. So what is the result of all this? I mean, if you're struggling getting colors or spot colors converted properly, or your designs are just looking incorrect, you know, I would definitely consider using spectral data. If you have designs that have a lot of transparencies, gradients, overprinting colors that are done in Illustrator, it's really, really the best way to go. Again, one of the other benefits that we have is that we're now seeing people go into multicolor. So quality spot conversions to multicolor, and of course it can benefit that. So spot colors going to orange, green, violet. Higher accuracy for prints and proofings. One of the big things is that, of course, that Mark touched on, is that especially using spectral data, it contains and supports different illuminations. So D50, D65, or if you had a custom illumination that you could actually add to that. And it's one library. So it's one library so if you had, say, a Pantone R32, you would have one library for that specific color. How does this translate into real life? Well, this is an example from one of our packaging customers over in Germany. And even though it's a Dutch product, it's cat food. It's a cat food container, and it's kind of interesting. It was a German printer, but it's actually a Dutch product, so that's kind of interesting. And what they wanted to do is they wanted to improve the overall quality of the finished piece. But not only that, they started to run into some issues with this particular job and the requirements of the customer. So a lot of times, obviously with conventional printing, if you're going to print 50,000 of something on an offset press, yeah, that's great. But sometimes the customer is going to come back and say, well, we just want to make some minor corrections to this. So this is kind of where the backstory comes into this. So this customer was struggling moving the job from a typical offset situation with plus spot colors. So they had an 032 and a Pantone reflex blue. And they wanted to move this to the indigo. Not to bash the indigo, of course, but they wanted to move it to digital. So two completely different kinds of processes. And the customer, like I said, had ordered a substantially smaller quantity with some corrections. And they wanted to print this job in orange green with the additional gamut expanding colors, so orange, green, and violet. And then they tried to use lab data to do that, and it was really kind of a struggle. And for those who are reading ahead on the slide, yeah, it was a struggle. They tried it with typical lab values. They tried manipulating it in pre-press manually, and it was just like a huge struggle all the way around. So what they did is, with the help of one of our color consultants over in Europe, is they decided to try to add a simple test chart. So what they did is they printed a simple 10 patch chart for both the reflex and the 032, and they printed that on the actual substrate that they were printing on. So what did they do from that? So it's kind of interesting. So the resulting data was pretty significant. They only ended up with a 0.9 delta E average with a maximum of 6.6 delta E overall. So only a difference in percentage of 2.8%. So if they go to the other way, which is they went without spectral data, and they tried that too, obviously, and the average jumps up to 3.4, which is almost 7%. So that's the minimum. The maximum is just off the charts, 11.9. I mean, no brand owner or company is going to accept 11.9 delta E off. It was just crazy. So, and one of the other things I like to point out there too is once they figured this out, so every time this customer then ordered, it was if they had the same substrate and whatnot, anytime that they had something that was printed with these two extra colors on that paper, they could also convert other jobs automatically because they had that data and it was stored. So this was actually a process with a color server without the pre-press department needing to make any kind of corrections. So it's also possible and practical if you're converting with this to introduce spot colors. Even with solid colors, it's going to be a huge, huge improvement. And just to wrap this up, really, there will be a significant improvement in your design for both accuracy and quality. And think about the color process, the color print process while you're creating the design. If you don't have color definitions, you're going to get unpredictable results when you print. Involve the print manufacturer at an early stage of production. Many print manufacturers, they have already gone through this stage. They already have things like Pantone Live implemented. They already have color servers. And for all the brand owners and designers that are on today, don't be intimidated by all the geek speak. Organizations like the Idealliance, they have the resources to help you understand this process. If not, there's many, many resources online, and all the different manufacturers have, committed to try to help not only the print manufacturers, but also designers and brand owners to help get the best conversion possible. And then lastly, I always say, because it's a big part of our business, is automate your color conversion. Many print and packaging manufacturers have already installed color servers like ours that allows for spectral-based libraries or CXF export data, of course, including the data in the PDF file. That can be done right now with the tools available, and it's really a tremendous improvement for your end product. Thanks again, and I'm going to hand it off to Ray, and he's going to talk more in depth about spectral data specifically.
So hopefully you're seeing my screen now. I want to thank you for being here, and I'm going to sort of walk through, sort of in the cleanup position, a little bit about spectral stuff. When Ron first asked me to do something here, this is sort of the series of topics he asked me to do, and I'm essentially going to drive to these answers, but perhaps not quite in the way that was originally intended, because, you know, in a sense, this is all the information you need. This is the first 2/3 of my presentation right here, is this data right here, which I gathered at my desktop, but perhaps it needs a little explanation. So I'm going to talk about metamerism a little bit differently. Up on the top here, we can see on the far left 2 inks that look darn near each other in D50. And so if you have a really nice projection and a good screen, maybe you can see a slight difference, but they're considered an acceptable match by most people. In the middle there, you can see suddenly I've changed the illuminant, and now those 2 colors don't look nearly like each other. And so we can imagine a situation where if I were specifying this in colorimetry, and so getting that answer on the left, and this was a color that was very important to, say, my package, and I printed this, and then I printed it again with a different ink and put them side by side in a store that miraculously wasn't using D50 standardized lighting, we might get a different answer. And in fact, we do. We can look at this. And so these are spectral curves. I think we've firmly established what those are at this point. But in this particular case, the 3 areas to look at are right there. When we see crossovers like this in 2 spectral curves, we can be pretty sure that there's a rocky road ahead if we're going to see this particular ink in more than, or a couple of inks expressed side by side in a package or some other design, and we're going to use them in more than one illuminant, or not in a standard, press side D50 illuminant, which, our whole world would be so much easier if everybody just carried out, everything in D50. But, in D50, this is essentially 1 delta E apart over there on the left. But the problem here is, we can see that as soon as I move this around, that's not going to be the case. This becomes even more important when I think about design and color relationships. On the left here are 2 series of colors formulated differently. So under D50, they may not have a perfect match to left and right, but they maintain a very similar relationship of each color to the next color from top to bottom. And so, if I were in D50, any of these would be fine, and if my relationship required any of these, they would look good between, say, the bottom of the package that had 1 element and another element and another element. The problem comes as soon as I, again, change something. So these inks on the left, this is the way the spectral measurements of all those inks are. And if we think to the last slide, we can probably see that there might be trouble in paradise here if we moved away from D50. And indeed, the inks on the right side were all formulated with the idea that they needed to move across and have good relationships to each other no matter what the illuminant was. And so, again, this is the kind of stuff that without spectral data, you just aren't going to know. And that's really the key piece here, because we can, as I think both Mark and Jim said, right, if we have the spectral data, we can go down and look at LAB, or we can look at density, or we can look at anything else. But has been the case often in our workflows, we've either never captured or we threw away the spectral data early, and then we couldn't get back to some of those other pieces of data and the kind of power that spectral data gives us as well. And in fact, since everybody's just been talking about how long I've been in the industry, I'm going to go here and talk about something here that was one of the first powers that I saw back when I moved from being a photographer to being on the print side. And this was this area about, looking at spectral curves again and then looking at ink, or is it paper, right? And we can guess maybe here that what we're really looking at here is paper. So this is one of the guides that's been put out over the years, looking at the same color being printed on different papers. And so visually you can see quite a difference down below, but you can also see up above, how the different papers, as Jim expressed, how the different papers can really affect the way that a color comes out. So, there's not a single attribute here when we talk about printing, right? That ink, its paper, its interplay all become very critical. But one of the nice things is if we have the spectral data, we can know essentially what that's going to look like long before we start mixing them up together. And that's really essentially the trick that we use in ink formulation typically today, right? So we have that spectral data, which gives us all this kind of flexibility, and we can predict what it's going to look on different substrates. We can look at it whether it's going to look like under different illuminants. So maybe we need something that looks good in, looks good at press, but more importantly, looks good in a store, looks good at home, and maybe actually you have two big stores that use different lighting, which is pretty common today, especially as stores move over to different kinds of very efficient lighting, either different kinds of fluorescence or now moving to LEDs. You can actually go and make sure that with the spectral data and then using those descriptions of illuminants, you can make sure that they're going to match as they go to these very different places, which becomes really critical. And then, for you, if you're making the process, it's also important to understand other things because different inks cost very different amounts of money, and of course you'd like to use up waste inks. And so you can know if you can do those things, use lower cost ingredients or use up waste, and whether that's going to adversely affect the quality of your product or whether it's going to have no impact on that other than be more efficient use of things and be better for the environment as well. So this is one of those things where if we had thrown out that data ahead of time, we really wouldn't know until it became too late if there was a problem. So that's really the takeaway for me is that spectral data really has to be kept no matter what we're using in the meantime. It's sort of like, we want to make sure that we keep all our data ahead of time. So we talked a little bit, and I sort of digressed, but it was one of the things that had been asked about is what's a delta E? Well, it's not really spectral, so we can just throw away the spectral data. No, I think hopefully we learned that that's not what we want to be doing. But on the right here, those are not patches that I whipped up in Photoshop or Illustrator or something like that. Those are patches that I actually took a picture of and rearranged here. So they're not perfectly illustrated maybe, but what these really are a series of patches, much like what we saw in a couple of other illustrations, but these are essentially one delta E apart from each other. So we should assume in most businesses the one delta E is good, and that's fine. But of course, they're one delta E under a particular illuminant. And that's one of the things to talk about, right? When we talk about metrics like delta E, we've reduced ourselves back down to colorimetry, which means that we're talking about it, under a particular color of light, and something we really haven't addressed and probably don't want to address in this seminar, but in a particular observer. So in print, we use a very narrow view, but in some cases, particularly as we expand the kind of directions that we're taking print, most of the rest of the world uses a 10-degree observer, which changes our perception of color as well. So these are the spectral curves of these, and we can start to see, sure, we see some differences in lightness there or reflectance, but we can also see in the curve, down the shoulder and toe of these curves, where some of these changes in color are happening. So if I were to overlay illuminants on top of here, you would see that in a couple of cases, illuminants would make these suddenly jump very far apart from each other, so that if it were very critical that I was correct under that particular illuminant, then I would have to actually deal with the problem in a different way. So delta E is an important metric, but understand that it's also limited as well. So one of the questions was asked is about how do I, so I have all the spectral data. We don't want to throw it away, but lots of times the most practical metric is, if I'm running a press, I might want to get density. If I want to do delta E comparisons, I want colorimetry. And so, how do I do these conversions from spectral to colorimetry? And of course, my answer is I'm lazy. So why do hard stuff if your instrument and software will do it for you already? I mean, that little chart magnified up here, that value came directly out of the instrument and I pushed it directly into a spreadsheet. So it's not like I had to actually go run a formula in the background of Excel. I can pump that into Excel directly from an instrument. Or Maybe I don't even need to pump it into a spreadsheet because the instrument will just tell me right there on the face of it. It's using Spectral behind the scenes, but it's showing me on the left side there, it's showing me density, it's showing me LCH. And if I want to know color differences, I can push a button and it's showing me, a nice colorful plot of what's going on and the differences. So I can see that, the L star isn't very big, and the hue difference is maybe not huge, but there's a big difference in chroma. So, that's what I need to worry about, right? So, how do I convert from spectral to colorimetry? It's happening all the time around us using the tools that we use every day. The next one is a blatant plug of a feature that I don't think half the world knows about who uses the product, so I'm going to make a plug. Sorry, it's a plug for something that's near and dear to my heart, which is profiling software. But one of the things that we have in our profiling software, and most other folks do as well, is the ability to take any patch that you've measured inside of the profiling software, and click on it, and suddenly you start to see all of that kind of information that you want. You can see, what the CMYK build of that was. You can see what it looks like, a little soft proof of what it looks like under M0, which is a tungsten light, or M1, which is daylight, M2, which cuts out the UV. You can see a little spectral plot, which reflects that same kind of data, where you can start to see that there's a little bit of brightener in this paper. So, if I look at it with M1, I'm starting to excite those brighteners. I can look at it, LAB values. I can look at it under different illuminants. I can look at it under different observers. So I can do all sorts of fun stuff with it. But could I do this if I didn't have the spectral data? And the answer is no, right? So, again, do you really want to know how to convert this manually by hand and do all this? Well, if you do, I'm still lazy, and I'm going to point you to somebody else to go do the hard work. Bruce Lindboom, I think, has done a treasure for our industry by putting this website out there. There's lots of calculators that you can plug stuff in directly. He's giving you spreadsheets that you can download if you really want to go do this by hand. And he does some other things that are pretty interesting. A few things that I'm a little less, sure about this dot gain from LAB or profile. I think we've got some metrics that have gone beyond that now in the standards. And in fact, that's what I'll talk about next. So, why isn't spectral data standard in all of the standards and specifications? And part of it is because it used to be harder than it is today. And part of it is because standards are really broad in scope, and so they want to do that. But certain things are, right? So we have defined standard illuminants. I've talked about them for the whole time I've been talking about here, but these standard A illuminant, which is a tungsten, or the D series, which are all the daylight illuminants, and the E series, which is totally theoretical but easy for math folks to do things with, fluorescent series, and coming very soon, I think, are the whole L series, which are a whole new set of LED standard illuminants. And standard illuminants doesn't mean that you can go down to the store and buy them. They're really mathematical averages more often than not of a color, so that we can use those as practical pieces. And then we have standards around how we measure them, right? Because I'm come from a company that does measurement stuff, among other things, and that's ISO 13655. But that's defining, as Mark was talking about, do we use 20 nanometer instruments, or do we cut it up more finely, to 10 nanometers, or do we someday, cut it up even finer into 5 nanometers? And that's cool spectral geek stuff, but in the end, ultimately what it just says is that as we move along in the graphic arts, we're getting more precise because the color requirements are getting tighter and tighter. I mean, what we need for the brand colors to be right is tighter today than it ever has been before. But that's part of the issue, right, is that a lot of what we've used in the past is colorimetry based on D50 and a 2-degree observer. So those are all standards, but that's really not the standard that we're looking at most of our brand colors in today. We're looking at there in production, but we need the spectral data to really evaluate what's going to happen in other parts. But we are changing that, right? So that spot color tone value, that's one of those things that now gives us the ability to look at spot colors and really get information about how to really quantify, tones of them in a way that requires either, I think it should only require spectral, but we give the ability to bridge that with the colorimetry calculations as well. Jim already talked about the CXF4, but the whole CXF/X series from ISO really helps promote a standardized way of communicating spectral data so that everybody can use it. And the last standard I really want to harp on just for a minute is ICC Max. I'm vice chair of the ICC, and this just got published as an ISO specification, and this is really going to be a change. It took us 10 years to fully embrace ICC version 4, and I think it's going to take 10 years before we fully embrace ICC Max, but we're going to see elements of this in commercial products starting immediately. And it's using CXF for data, but what it really does is put spectral data as the foundation, which means now automated color management can do this in a very normal way, and you can get those powers of worrying about illumination, worrying about different kinds of measurement, worrying about all the things that happen when we move to new substrates and things like that. And it also allows, in some cases, ways to quickly make changes using algorithmic profiles that say that if we made a quick change on press, we can use that in a way to really update that and produce the right work. So that's a fast way to go through really all the power that a spectral data can give you. But if you look at those curves, you can see in the end that you don't want to throw it away. You want to make sure you keep it. And I'll turn it back to hopefully we've got questions.
Yeah, thanks
Ray.
a lot. Thanks for we actually have a lot of questions that came in, and we're short on time and want to be respectful of everybody's time that joined this call. So I'll just jump straight in. So if I'll give you the questions, if you can short, quick answers, that'd be great if you can tighten those up. So first question is, how does spectral data encode the hint level of a color? Anybody can answer that question. How does spectral data encode the tint level of a color?
I guess I'll go first since I can go first. You can measure anything with spectral data. It can be a tint, it can be a solid, it can be an overprint. It doesn't know. All spectral data is getting the raw DNA. Now, if you want to convert that into more, quote unquote, user-friendly metrics, you can convert that into tone value. You can convert that into spot color tone value. You can convert it into other things. But really, a similar question people always ask me is, how do you measure the dot area or the tone value of a stochastic screen? And, the answer to that is the spectrophotometer does not know what you're measuring. I'll stop there, and Jim and Ray can add or subtract if they want.
Yeah, I'll just say the same thing, but in one way. It's measuring what's in front of it. Things like tone value are calculations that we can do with the same data.
Okay. That's fine. I don't need to add anything to that. That's exactly right. It doesn't know. There is no discerning factor.
What is the rule of thumb about how many times two spectral curves can cross and still hope for minimal metamerism? I think maybe Jim, you answer that one because you were speaking on metamerism.
I'll answer it the other way. If it crosses three times, you're in trouble.
Yeah, I was going to say. Yeah, that is really the case. I wouldn't say you want to cross that many times. That's actually something I don't know if I want to really get into deeply, because it's actually it can be a pretty complicated subject. But go ahead, Ray, if you want to add anything, be my guest.
No, that's really it. If you cross it three times, you're going to be in problems. If you cross it less, you have to understand what illuminance you're going to be looking at, because then you need to see where the crosses are occurring and how big they are.
Great. And I think we have time for one last one. Is there software available that can import a spectral color curve and spectral paper curve to generate a curve to see what the paper does to the spectral color curve?
Our product Colorant does it. I know I1 Profiler does that as well, right?
Yeah, and ink formulation does that as well. If you need to worry about your substrate and your inks, that's part of the story, right? Mm-hmm.
Yeah, I'll just add that one of the advantages of true spectral measurement, there's different methods of compensating for paper color. And the ones that are based on true spectral measurement work better than the ones that are based on LAB.
Mm-hmm. Yeah.
Right. So we're gonna, as an industry, we're gonna update. You know, the Idealliance supported substrate correction based on the something called tri-stimulus, linear tri-stimulus substrate correction, which was a good thing at the time because it only needed 3 numbers, LAB or XYZ. But it's limited in how good it really predicts what a change in paper color will do to all the other colors. Mm-hmm. And when you get into true spectral, the math that they have in color and the math that X-Rite has and the math that Esko has, it can do a better prediction on how a change in paper color will affect all the other colors.
Yeah, that's really like kind of a rule with our tool. A lot of users, they like to mix. I see users mixing lab and spectral data, but I mean, really, our software would perform best when you plug that spectral data in from a substrate.
Well, that's great. And appreciate, again, thank you everybody who joined the webinar today, and thank you especially to our panelists who give their time. Anybody who has any more questions, feel free to shoot them over to Idealliance. We'd be happy to answer them all. And everyone will receive, who have signed up for this webinar, will receive a copy of this recording as well. So thanks so much. I hope everybody has a wonderful weekend. And if you want me to find out more about us and everything we do, please visit idealliance.org. Have a great weekend. Thanks again. Bye-bye.
Thank you all.
Thank you.
Yep. Thanks, guys.